Okay, as we proceed on, what we're going to do is we're just going to break down the engine's different systems and functions and really examine them. So we just did the lubrication system. Now we're going to do the cooling system. And we're going to talk about engine cooling and why that's important. So first on our list is reciprocating engine induction and cooling system theory, components, and operation. So we're just going to give like kind of an overview of the whole system, of the why, and then we're going to talk about on a high level overview kind of some of the components, and then we'll go into a little bit deeper. Okay, so this is a typical engine cylinder. One of the most iconic things on the engine cylinder is the cooling fins. And now you notice that the cooling fins go all the way around the entirety of the cylinder. One of the things that you'll look for on an annual is to see if the fins are broken or damaged or in some way, shape, form, or fashion. So what do they do? All right, so essentially inside of the engine, you have a controlled explosion. And in the case of a reciprocating engine, it's multiple explosions that are happening very, very fast. And those explosions are going to generate a flame. That flame is going to get the internal temperature up to about 2,000 degrees. They can be extremely hot. And so in order to control that heat, we have to have a layered system to help remove the heat from the aircraft. All right, so what happens if we don't do that? Well, one of the things that could happen is the engine could experience warping in various places. I think engine metal gets hot and it's under pressure, and so it's going to start to bend. Just like if you were to take some water and put it on a piece of 2x4 and then heat it up and then bend it, it'll actually start to warp the wood. And that's how they do like woodwork warping, things like that. Metal is no different. Matter of fact, it's probably easier to warp metal than it is to warp wood, or maybe. And so you get this thing hot, put it into a certain kind of configuration or do some sort of repeated action on it, and you're going to start to shape it and mold it into a new form. And we don't want it to be a new form. We want it to be in the form that it was meant to be in for it to operate appropriately. So warping is one of the other things. Another thing that could happen, and that will happen, is that it'll break down engine oil. Now, to a certain degree, we want that to happen over a set period of time, but we don't want it to happen too fast. If the engine oil or the engine is too hot, it's going to break the oil down faster, which is going to lose its ability to cool the engine. As it loses its ability to cool the engine, it's just going to make it hotter and hotter and make the problem progressively worse and starts to build on itself, and we don't want that. The other thing is that most pilots will probably complain about engine heat is the reduced fuel efficiency. Cooler engines burn less gas and get the same punch for it. One of the things that was real popular to do, at least when I was in high school, was to put a cold air intake on your engine. You can still get them. Usually there's basically a K&N filter that help bypass your engine airbox. And what that basically did was bring cooler air in. You think that the air, think about your basic physics, the hotter it gets, it wants to expand. Well, you want to have those molecules closer together, because for every one molecule of air, you get a molecule of fuel. You have that 1-to-1 ratio. So the tighter you can pack them in, the more fuel you can get into an enclosed area. And as you can see, you're limited to the amount of area that is that you're going to have on any one cylinder. That being the case, that the cooler the air coming into it, the more efficient and the more power you can produce at a lower RPM, and so or at a lower fuel burn. So therefore, like, the hotter the engine gets, the less efficient it becomes. The less efficient it becomes, the more expensive it is to fly from point A to point B. Okay, so this is going to be the basics of how engines cool. Liquid or air is fine. All right. So you have a hot surface. Okay. Then you have cool substance. It could be cool air. It could be cool liquid. Doesn't really matter. All right. And what's going to end up happening is that you're going to have little, so we call molecules of heat. They get super duper hot. Okay. Now, because heat wants to be dispersed, it wants to push out and go all over the place, it's going to want to come over here to this cool surface. Well, there's cool air over here, and it wants to start to balance it out. so that heat starts to jump off. That's why radiating heat works. Like you can get something super duper hot and put your hands on it, you can feel that heat coming off because there's an imbalance. There's a lot of activity happening here, not a lot of activity happening over there, and that starts to jump off and come there. Same idea with like your electricity. So that way, like you have like a bunch of electrons here, you walk by, it arcs you. You have a static jump. And that's same kind of concept. It's just now it's happening with heat. So whenever we look at our engine, you have a cylinder with all these cooling fins. Either way, all we really need to do is give that heat ample opportunity to make that jump. And so we do that by increasing the area in which it can jump from. So you can go from on the cylinder into the cool air. You want to expose that cylinder as much cool air as possible. So if you think about it, a smoothbore cylinder like that has like an area of, we'll call it 2, all right? Well, how do we increase the surface area of that? Well, if you really kind of think about it, like the only air that is actually touching is whatever's right next to that cylinder. What we need to do is have a bigger cylinder, but we can't do that. You'd run into a whole lot of other problems. But what we can do is increase the surface area of that cylinder, and that's what that cooling fin does. It creates all this extra surface area for air to go around, and it does it right here, and does it right here, and does it right here, and it goes all the way up until where it was a surface area of 2, now it's a surface area of 10 or more. What we've effectively done is create all those little fingers for air to pass through, but you haven't really increased the size of the cylinder at all. That allows for that air to pass through there, grab those little heat molecules and pull them off. That's how we regulate heat. And that can be done with either air or liquid-cooled engines. We'll talk about that here in just a minute. Let's go look over some components, then we'll start to put them together. All right, before we get too much further in there, let's just talk about temperature. Let's talk about like the different places that we measure temperature and why we measure it and why it's important to keep it in its proper range. Okay, so let's talk about the various temperatures that we may encounter when we're all working with the engine. The first one that we're going to run into is oil temperature. Now, oil temperature is obvious. Like you want that oil to stay at a certain rate. You don't want it too low because then it's going to be really viscous and not really move around the engine, not do its job. And it's also going to indicate that it's not circulating, because if the engine's running, it's hot. The oil should also be running, and it should also be just as hot, or at least close to it. And so we're always going to pay attention to that. High oil temperature is going to cause the oil to break down a lot faster. It's going to cause potentially the oil to catch on fire. It's not going to lubricate and clean and bring that temperature down if you keep running it at super duper high temperatures. It gets too high, basically turns into an inferno, so we don't want that either. But that's oil temperature, something that we're going to pay a lot of attention to, and the cooling system is meant to help lower that oil temperature. One of the ways that, let's say if you have like super high engine oil temperature in flight, you're going to nose that plane over and increase the airflow over the top of that engine to help try to drop that oil temperature back down. Next is going to be the cylinder head temperature. Now, cylinder head temperature is interesting. It's becoming more and more popular, more and more relevant with the invention of modern avionics and like ICAS systems and stuff. They can monitor engine health. What you do is that you'll have a probe on every single cylinder, and it'll give you a readout in the cockpit of like, hey, look, this is what the exact temperature that this cylinder's at. So in the old days, it was like all you really had was just engine oil temperature, and that was about it. Nowadays, you have a digital readout of like, hey, look, here's the overall like engine oil temperature, but here's every single cylinder's head temperature. And that lets you know that, hey, look, this cylinder is running hot. And then you can ask the question, why? What's going on with that one cylinder? Something's not right. It's not cooling correctly. There's something not correct there. And you'll see guys that will ask for A&P services, say, hey, look, my number one cylinder is just running way hot and I can't figure out why. Please come help troubleshoot it. And you'll get in there and you'll look. Usually it's something technical that unless you had a trained eye looking at it, you would never see. But it's the cylinder head temperature. It's often abbreviated CHT. You'll see that a lot of times in pubs. You'll see that on displays, or cylinder head temperature. All right. The other one is exhaust gas temperature. Now, exhaust gas temperature, literally as the exhaust gas comes out, that's the temperature that's going to read. Most of the time, this is going to be a really big deal with turbine engines. It still gets monitored in some reciprocating engines, but largely you're going to spend more time monitoring your oil temperature than you will EGT, and you definitely will probably spend more time with the cylinder head temperatures than you ever will with EGT. However, that being said, you may still see it on some aircraft. And that EGT, all it is as the exhaust comes out, it tells you what temperature the exhaust is. That indicates you how hot is actually going on inside the cylinder. You keep in mind the cylinder may get up to like 2,000 degrees, but like EGT is going to be like 600-700. It's going to lose a lot of heat as it just moves out of that cylinder, but it's still really hot. It's hot enough to do a lot of things. High EGT it could be an indicator of an improperly run engine, improperly operated engine, any number of things. So like it's best to just go off whatever the maintenance manual and the POH says to monitor that EGT and know what the next step is. If this is just normal or is it too high or whatever. And on top of that, as long as you've done your annual and you've made sure that the engine is the EGT meter is reading correctly on the dash of the plane, you should know if it's in the green or in the red or in the yellow or what have you. All right, the simplest component that you're going to see over and over again are the baffles on an engine. I actually had a guy call me just the other day asking about his cylinder head temperature was a little bit high, and he thought maybe a baffle problem was it because they had just done some service on it, and he thought whenever they put the cowling back on, it had messed up a baffle, causing the air not to flow correctly, therefore causing the engine to be hot. And I told him it's probably true, and I'd be happy to look at it for him. But all that the baffles really do is just simply direct the airflow where it goes. So let's talk about engine baffles. Okay, so when we talk about engine baffles, what we're talking about is this like little rubber wall here, for lack of better terms. Baffling simply just takes the air that's coming into the front of the cowling and then channels it into this area. Now it's sealed with the cowling sitting on top of it, and that creates a high pressure area because as all that air comes in, it starts to build up pressure, and it has to go somewhere. And where it goes is through the cowling or through the cooling fins on the cylinder, and then it goes out the bottom, and then out the bottom of the cowling on the bottom. And this creates a channeled airflow for the engine heat to escape in. Now, baffling being wrong, like it's damaged or otherwise messed up, can cause heat to build up inside of the engine and damage it. So one of the things to look for is that if you have high temperatures, the baffles could be simply messed up. That's usually the simplest and easiest thing, especially on older aircraft. That as the cowling comes on and off, they get worn or torn or whatever, or they don't seat properly, and that creates a air leakage, like say like right through there, and that air comes out and it degrades the amount of air that's going over the cylinders, causing the cylinder temperature to rise. And it doesn't take a lot; just a little bit goes a long ways with this. What is an augmenter cooling system? What does it do? Where are we going to see it out in the field? Now, even at the very end of the paragraph on augmenter cooling systems in the 8083, it states that augmenter systems are not used much on modern aircraft. They just kind of fell out of favor with most aircraft designers and owners. But if you ever run across them, we're just going to read out of the 8083 what they are. Augmenters use exhaust gas velocity to cause airflow over the engine so that cooling is not entirely dependent on prop wash. Basically, they squeeze hot air out the back, and that vacuum that the hot air creates pulls air through the engine. Vanes installed in the augmenters control the volume of air, and these vanes are usually left in the trail position to permit maximum flow. They can be closed to increase the heat for the cabin, or anti-icing used to prevent the engine from cooling too much during descent from altitude. In addition to augmenters, some aircraft have residual heat doors or nacelle flaps that are used mainly to let the retained heat escape after engine shutdown. The nacelle flaps can be opened for more cooling than that is provided then by the augmenters. A modified form of of the previously described augmenter cooling system is used on some light aircraft. Now, I will tell you, I've been working on airplanes a long time, and I literally had to call people to try to figure out what they were talking about here because I've never seen them. And even, like I said, the 8083 tells you that they're not, that common anymore. Okay, this graphic is going to show us exactly how it works. You notice that you have the yellow arrow shows the air that's coming into the plane, and then you have the exhaust that's going out. And what that heat moving through there basically grabs that ambient air and then pulls it out, creating a flow. And this is what the 8083 says about this figure. So the engine is pressure cooled by the air taken through the two openings in the nose cowling, one on each side of the propeller spinner. A pressure chamber is sealed off on the top side of the engine with baffles properly directing the flow of the cooling air to all parts of the engine compartment. Now, this is just like a Cessna 172 or a Cherokee 140 or whatever. Works exact same way. Warm air is drawn from the lower part of the engine compartment by the pumping action of the exhaust gases through the exhaust ejectors. This type of cooling system eliminates the use of controllable cowl flaps and ensures adequate engine cooling at all operating speeds. Now, I'll tell you, like I said, this is not very common anymore, and now people just mainly use cowl flaps, and that's about it. I've yet to see an augmenter cooling system on any aircraft. There's going to be on some older ones, but still not very common. Few, but some aircraft are actually liquid cooled, like your car. Let's kind of give a theory of operations for liquid cooling and why it works the way it works, and when could we potentially run into that, and on what types of airplanes. All right, this is another niche place where you will see these likely somewhere or another, but they're only going to be on very, very unique aircraft. Most of them are high performance in nature. Some of the high performance fighters in World War II were liquid cooled, and to their detriment, because if you took a bullet in the coolant system, the engine overheated and he crashed, and so it became very quickly an incentive to not do that. Liquid cooling is fairly straightforward, and I'm going to go over it with you here on a board, but just know that you probably are not going to see this on a regular basis. Almost everything in aviation is air cooled. Okay, so liquid cooled engines work just like this. You have your engine. All right, so engine does engine things, normal engine operations, except for you have up front a radiator. Now, you should be familiar with the radiator. It's in the very front of your car. If you go out there and you look at it, you see the little wavy fins. Those are radiators. All right. Now, in this radiator is fluid. You think about servicing your radiator on your car, or it'll if it gets hot, you can see it on the movies, or you maybe in real life, how they'll boil over and there'll be steam and stuff going everywhere. That's because the radiator it's got too hot, so it's causes the liquid to boil and it produces gas, and then off you go. All right. The radiator essentially will run coolant through the engine in different channels. Different engines accomplish this in different ways. And what happens is that coolant gets really, really, really hot. And then it comes back into the radiator and it starts going down all those fins. So those fins go back and forth, and they're really, really, really thin. So remember with the cooling fins, we increase the surface area, and the increased surface area helps heat bleed off faster, all right? Because you're squeezing that fluid down and allowing those little heat molecules to just disappear, go off into the cooler air. All right. When it gets to the bottom, it should be sufficiently cooled off, and it's ready to absorb more heat. And then it goes back into service, and it goes back through the engine, and it comes back to the top. Now, this is a basic principle of life, really, because you're going to see this same thing pop up in HVAC systems. You're going to see basically the same thing with air cooled, that you just have two different mediums the two different temperatures that are coming close together, and they're doing a heat exchange. So you hear talk about a heat exchanger. That's what they're talking about. Yeah, so that is how a liquid cooled engine works. Now, most aircraft almost always will use air cooled engines. And the reason being is that like it's more effective, it's lighter, it's a lot more reliable because it's just basically the way the plane's built. It pushes air into the engine and then down over the cylinders and then out the bottom, and then that's where the heat goes. No need for a bunch of extra stuff. Now, the things where liquid cooled engines beat air cooled engines is that like they're fairly constant. If the engine's running, it's cooling itself. Whereas with a air-cooled engine, you really need some forward airflow to help cool that engine off. Whereas with this one, you don't, because the air is not effectively the thing that's really cooling it. You can supplement behind the radiator a big fan. Very popular Jeep mod is to put, at least back in the day, like whenever everybody was running around with little YJs, you'd put a electric fan out of like a Cadillac behind there, rig it up, and then whenever the Jeep started getting hot, you turn the fan on, it would pull that cool air over the radiator and then drop it back down. Same thing. So like if you're sitting there, taxiing, you don't have enough airflow coming over that radiator, you can flip on a switch, close the relay, turns the fan on, boom, air just comes all over that radiator, dumps all that heat out in the bottom. But you have that extra weight, that extra complexity, all that good stuff. So you have to kind of weigh your benefits when you're designing an airplane. And the liquid cool engines literally just kind of didn't make the cut on most aircraft designs. Now, some of them that are, some of the newer stuff, you're starting to see some light aircraft, like the Jereboos are having like liquid cool heads again. Some high performance racing engines where they want to get the cylinder head temperature down to make sure the fuel atomizes appropriately, and they can also combat the excessive heat that those high performance engines put out. You'll see some of that, but generally speaking, this is kind of not the thing that you can expect to see out there. Almost 90% of your aircraft you're working on will be air cooled.